Okay, I think today is going to be better because the weather is better. So last time you were doing equality, and as I said at the end, I feel a bit rushed. So to unrush ourselves, I recorded a video showing how you prove that the length is preserved by reversal of lists. So this is this example here. So today, we're first going to revisit some equality examples because I really want to record equational reasoning. I think it's almost impossible to show on paper how to do equational reasoning. It's really interactive, and so it's better if you see it. So that's what we're going to do at first. And then we're going to go and look at a new construction called dependent sums and record types. Okay, so this is already on the video, so I'm not going to do it again. So we'll just go straight for the next example. And I want to show a little bit about how one goes around building equality proofs. So I'm going to open a separate file for this. I probably think I have it. No, I have the length reverse full 3 like that. Just so that we're not detracted from the text surrounding text. So how much do I want? I want this. I want this. Okay, so this much at first, and full 3 needs to be now called full 3. And okay, when you take things out of other files, of course, you should expect some problems here. Okay, like that. So let's recall, I think this was in the exercises. So let's recall the definition of a binary tree whose nodes are labeled by elements of A. So this is an inductive type. There's a base case, which is a leaf. You could equivalently think of this as an empty tree if you wanted to. It doesn't really matter, but let's think of it as a leaf, which is not labeled, and then nodes. A node takes a tree, that's the left subtree, the root, which is labeled by an element of A, and the right subtree, and then that constructs a tree. Okay? So how would we calculate the depth of a tree? So the depth of a tree is calculated recursively. So what you write is, okay, we're going to have a function called depth. It takes in an A, which is implicit. It takes a tree, and then it returns a natural number. I can probably make this still slightly bigger. I'll have to make the font smaller if I start running out of horizontal space. So then we just do it by recursion, right? So the depth of a leaf is 0, that's the base case. And then if I have a node with the left and the right subtree, that's 1 plus the maximum of the depths. This thing here is the max. It's defined for natural numbers. Let's have a quick look at it. Okay, so it's a function. It says the maximum of 0 and n is n. The maximum of successor and 0 is the successor m. And if you have a successor and a successor, it's the successor of the maximum. So this is not at all surprising, I think. Okay, so just to have some trees, let's define what a full tree is. So a full tree of rank of level n is just the binary tree that always branches by 2, 2, 2, 2, 2, right? So if you go down to rank n, you're going to have exponentially many. It's going to be something like 2 to the n plus 1 minus 1 nodes, something like that. So the full tree of length 0. Oh, also we need to put something. We need to label the nodes with something. So this function actually takes an element of A. That's the thing that we're putting in the nodes. So all nodes will be labeled with the same element. And this is the depth to which we want to go. So if the depth is 0, then we just say leaf. If it's a successor, then we make a node. We recursively produce two full subtrees of depth 1 less, and we label it with x. Questions? So this, I would hope, is clear how this is going to make a tree that is, looks like this is going to be x, and then it's going to be x. There's no reason for me to draw such small things here. X. So this is now level 0, 1, one more. Well, now, unfortunately, since I did one more, I have to do one more because it has to end with leaves. So leaves are not labeled, so there are now leaves here, okay? But you just keep doing this sort of thing. It's with an N. That's some bad planning. It's okay, yeah? Ja, lahko. Tole niso časovne vrste. Wrong course. Okay. Still bad planning. Okay. Yep. Kako boste pa zvedeli, kam greste? Ja, dvomam, da imamo dvoje časovne vrste, tako da če ene najdete, sta verjetno ta prave. Okay. Well, they're not going to learn any Agda today. Okay. So that's a full tree. Now, let's try to prove something that we believe in. So where is it? The other buffer. Here. Let's prove that the depth of the full tree is actually what we think it is. So this is the part that I'd like to show you. Yeah, so this is a bit too much. So let's try this much of the depth. And I can increase this one down here. So given any set A and an element X and any N, there's really no need for this arrow here, so it could be without this. No. Now it wants an arrow. Wait. Oh, no, it's okay. The arrow is not needed, but there are other problems. It's that this thing has at the top an open import, which then therefore this thing needs to have. Okay, so now it's working. Okay, so given any x in A and any n, the depth of the full tree actually equals n. So how does one do this? So you go and you say A is implicit, so we're going to leave it alone. We'll put it in only if we need it. We get an x, we get an n, and then we have to prove an equality. And so then I go here and I say, what to do? Show me the goal. As always, keycaster. Do you think this keycaster thing is useful? It's probably useful for people on the video. Okay. So how do you do this? The first piece of advice is that you want to do this on paper, or at least you have to have some idea of how you're doing, especially if you're not well versed with the proof assistant. So my experience is that the combination of not knowing exactly how to prove a thing and not really knowing how to use a proof assistant well usually ends in disaster. So, or not a disaster, but just some unnecessary confusion. So it's always better to have some idea what it is. You have to know one or the other. Once you know the proof assistant really well, then you can use it in a way that helps you direct the proof. So here, we're going to first, let's think for a moment, is this supposed to be difficult or not? Okay, so we can actually just go and see, well, okay, so we need a plan. So what would be a good plan? So the good plan would be this. You look at your types and your functions that are involved, and you think about how they are defined and constructed. So trees are inductive. Because trees are inductive, one possibility would be to have a induction on a tree. Then n is a natural number, so we could also have induction on n, right? That's another possibility. Now, of these two, okay, x, there's nothing we can do with x. Now, of these possibilities, we can't really do induction on the tree because the tree is not an input, okay? There's no tree that we can induct on. It's only on the left-hand side of the thing we're trying to prove. So it would make more sense if it's going to be induction. It's going to be probably on n. So I would actually try to do this also because I suspect that the proof will go by induction. I mean, after all, if you prove that the depth of the full tree of level n minus 1 really equals n minus 1, then it should be possible to prove the next level, right? So let's do induction on n, so which in AGDA just means Control C on n. Okay, and now we have the 0 case and the successor case. And the 0 case is showing us, well, you have to prove that 0 equals 0, where AGDA decided to use the nice notation in one case and the 0 constructor in the other case. This is a typical sign of software that is, that has not been invested in by Apple with $1 billion so that it would look really nifty. So this is what you get if you just pay some Swedish students to make software. They try their best, but this is what happens. Okay, so this should be easy, and whenever it should be easy, I try Control C, Control A to see whether AGDA can do it, and it says, yeah, that's just reflexivity. Actually, the two sides are actually equal, so no problem there. Okay, so this one is going to be more interesting. So you stare at this one, and you say, hey, how are we going to do this? And you say, well, this thing in here, by induction hypothesis, I know that this one should be n. So if I make a recursive call to my function, it will tell me, it will give me an equation that that thing equals n. So I have a plan. My plan is going to be that I want to, well, there are a couple of things, there are two things I really want to do. I want to replace depth full xn with n by induction hypothesis. That's one thing I want to do. But the other one that I see here is that actually I have the maximum of two equal expressions. So, well, the maximum of n and n of x and x is x. So in fact, there should be a lemma somewhere in the standard AGDA library, I hope, that will say that the max of n and n equals n, and I would also like to use that lemma. So maybe I don't know what the order will be of applying these ideas, but I do know that I want to do, that it's going to be at least two steps of reasoning, right? I will want to do one thing, then I will want to do another thing. So for that kind of thing, I use the reasoning notation, which is this begin-end business. And the reasoning business is in the submodule of this module. It's called equal reasoning. And the way that you work with this is I want to open it so that it will be available to me. So I could open it up here. That would work. But now it's open for the rest of the module. We should practice opening things only when they're necessary. So you can have a where clause and an open statement inside a where clause. And then that means that it will be open up here. I know it's ridiculous, but it's equally ridiculous to define things with where after you use them. So why not also open modules after you've used them? So let's do that. So now I created the possibility that now I can use whatever is in here. So the thing that is in here is called begin. So that's the one I want to use. I say I begin making an equality proof. There we go. I think maybe I have, is it like this? It's possibly like this. Yeah, it's a prefix operator, so you have to say begin underscore, okay. And now I say I want to make a chain of steps. So to make a chain of reasoning steps, you need to use this operator that is called equiv, and then you give a bracket. So it has this form. Let me put in question marks. It has this form. It says left-hand side, the way that this works is left-hand side equals right-hand side for the given reason. So you give the reason here, okay? And so let's just say we will use this, and now it does these parentheses, which are not really necessary. I mean, we really are grateful to the Swedish students for having implemented this, but we do need to do things manually every once in a while like this, okay? So this is how I like to put it. And now, we already know, so we will start here with the left-hand side. So this is going to be the left-hand side. And then we'll make boop, 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 and we'll get to the right-hand side. I don't have to copy the left-hand side because it already knows what the goal is. If I ask it, so it says, okay, you have to give me the thing you're starting with. But I can tell AGDA, say with Control C, Control S, you know what it is supposed to be. It is, if this is going to be a proof of this thing, you have to start with the left-hand side. So Agda knows it's the left-hand side. So Control-C, Control-S actually said, yep, it's left-hand side. So now I have to think what I will do with this step. You see, it's saying, okay, this is your left-hand side, and now you need to give me a proof of that this left-hand side equals something. So what would we like to do? Okay, so let's first, this thing here, let's first make sure that we have just one depthful xn. So we are going to use a lemma that says that x max, the maximum of x and x equals x. I want to use that. There are two problems. First, I have to find the lemma. And second, I have to do it under the successor. You see, I have to do this. I have to apply some lemma under the successor. Whenever you want to apply something under a function or under a constructor, the thing you do is you say conc. Conc is the thing that goes underneath, if you remember from last time. Conc, and then you can press I can submit this with Control-C, Control-R, but I already know what this one is. I have to tell it under what? I say under successor. So I submit this, and it says, okay, fine, you're going to argue under successor, and if I look at what is the goal here, you see now it's without the successor. Okay? So if you want to go underneath, you do this. So now I continue, and I say, okay, I need the lemma. How do I find the lemma? So in the video on Monday that I recorded, you saw that I couldn't find the lemma. So let me try if it works today. I still have no idea why it was like that. So I say, show me lemmas involving this thing. Okay, I'll really have to debug this. So I'm going to go in here, and I'm going to look for, nope, it's not here. Okay. So in the interest of not losing too much time, I will cheat, and I will look for the lemma in the solution. Okay. So it doesn't have it's not a very surprising name. And so let's see, okay, there is no solution better than to fix my Control-C, Control-Z. I really need to figure out why it's not working. Because, maybe I haven't opened the right module. It says there are no lemmas about plus, which is ridiculous. But I did open, it's here, data nat properties. This is where I would look for it, not the equation. Okay, so this is about natural numbers. Okay, so now I go and I say, show me, I just randomly look for square cup. Properties of, excellent. And now I go through this, and there's gonna be a lot of them. And they try to have mnemonic names and so on, so which is very good. See, la 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 la. And it helps that as a mathematician, I know what the property that I'm trying to prove is. The property I'm trying to use is that max of x equals x, that's idempotency. Okay? So because that's idempotency, I could also use idem, and I will find it. So I find a candidate lemma, but it's not really clear what this is doing. Okay, idempotent something. Nevertheless, I have a candidate. Now that I have a candidate, I put it in here, and I say Control-C period, and it says, okay, the thing that's in your brackets here has this type. Okay, this is not very helpful. So I press Control-U, C period, which normalizes that type. It computes it. And now I see, this is exactly what I want. Okay? It is the max of x and x. So I submit this with Control-C, Control-R to say, I want to use this. And it says, well, you can use this, but now you have to tell me what you're applying it to. But I think Agda should be smart enough to figure it out. Control-C, Control-A. No, it's not. Well, okay. Control-C, Control-S. No, it doesn't want to. Well, it doesn't want to because it was what? Depth something, right? It was depth full xn, if my memory serves me right. Okay, that was the right thing to do. So I now made one step of reasoning. Usually people format these equalities in two ways. Either they do this for this reason equals that, and they keep the term and the reason here, or if they're running out of space, sometimes they do it like this. Okay, and so then the next equal sign would go here. It really, you just have to pick a formatting style. Okay, so now let's see what we need to do. So now we got rid of the double depth. Now what is my next step? Well, my next step is that I want to use the induction hypothesis and replace this with n. Yes? So how do I do that? Well, it's a similar story. I want to use this equiv business, which I could also type it just out here, like this, make some holes, okay, and say, okay, this is what I want to do. And Control-C, Control-S will again put in the thing, it can compute what this is, so it's computing it. So now what do I want to do? I want to make a recursive call on this thing, so let me do that, and it's under successor, so I know it's conc-suc, like this. Control-C, Control-R, and it says, what do you want to do? And I say, well, I want to use the induction hypothesis, which is depth full of x and n. And I submit this, and it's happy, and for some reason there is a space here. And so now I say, what do you want? Oh, I'm done. Well, now that I'm done, I say QED. Okay? And then I say, finish this off, you know what it is, boom. And usually people put QED down here. So that was an example of how to do equational reasoning. Yep. Okay, there's one more. The one more is more involved. So let's do the more involved one together. The reversal of concatenated lists. This one I think is good to see because it requires, well, it requires formulation of lemmas. So let's do this one as well. Now I'm going to face the same problem. Okay, we will need the data list. What else do we need? Open, import. We'll put them up here. So I know I want this. I know I want, I want this one for sure. There are no natural numbers, I think, involved. Just to set things up. Okay. So this is like a reversal of lists, but it's a slightly dumber function. We did reversal of lists using accumulators, and here this one is more naive. It says the way you reverse a list is that you reverse the tail, and then you concatenate that with list of length 1 that contains the head. So this is a quadratic algorithm instead of a linear one, but nevertheless it'll be it's slightly easier. Well, it's actually a great deal easier to reason about this one. So let's try to prove something about it. Where was this? Okay, I want to start here. So let's read what it says. It says, given any two lists of x's and y's, how do you calculate the opposite of the concatenated list? It's the concatenation of the opposite lists, but you also need to reverse the y's and the x's. Yes? Like that. Okay. Okay. You write this, you say, okay, x's and y's are here. I will put in a if I need to. And now you take a deep breath and you say, how are we going to do this? Okay, what are our options? Okay, first of all, we suspect that it's going to be an induction, right? But there are two possible candidates for the induction here. We could do an induction on the list of x's, or we could do an induction on the list of y's. You need to guess which one is the better one. So that's one thing. Now, how would you guess that? You have to go and you stare at the definitions of opposite and plus plus. Yes? For instance, if I want this thing here to compute, then I would need to look at the definition of plus plus, and the definition of plus plus recurses on the first argument. You see? It recurses on the first argument. So if I want that thing inside to calculate, it better be the case that I'm doing induction on the first argument as well, because otherwise it just won't compute. That's one option. But there's another option, which is that maybe if I do induction on the second argument, then maybe this one will compute nicer. I don't know. I have to think about this, okay? So I have to take a lucky guess sometimes. And in order to waste a lot of time, we're going to pick. It was the first argument after all. Okay, so let's try the first argument. Okay, so this is as much help as I will give myself. From now on, we should just be able to do it. Okay, so we're going to do induction on the first argument. The reason being that in that case, it's going to compute in here, because this one does recursion on the first argument, but it's not going to compute here. So I expect that I might have some trouble because this side won't compute when I do induction on the first argument. I may have to prove some lemmas or something. Okay, so I look at this and I say, this case comes down to the opposite of y's is the opposite of y's plus the empty list. This is now precisely the problem that it doesn't want to compute. I can say, please compute. I say normalize, and it says, well, okay, this is how much I will normalize for you. And this is kind of weird, but okay, sure, why not? So it didn't really, it's not REFL, it's not the same. Okay, so is there a lemma that you would suggest that we prove here?
Having an empty list at the end is the same.
Yeah, attaching this, concatenating the empty list at the end is the same list. Because it's totally unimportant that this list is opposite of y's. It could be anything. Okay. So in that case, you say, oh, I want a lemma. So if you want a lemma, where will I put the lemma? Okay. So I can put the lemma here. I start putting it here. Where? Okay. But I could also decide that it's kind of useful to know that attaching the list at the end is something that we want. I could also search the module. I could also search the library because it's very likely that the lemma is there. So anyway, let's put the lemma here, thinking this is kind of useful. And so this says now, if I have a list of a's, then I want to show that z's is the same as z's plus like that. And it says, okay, you need to prove this. But before I prove this, I want to make sure that this is the lemma that I really need, because I don't want to be proving a lemma which later on I can't use. So I say, please apply this lemma. And it says, yeah, I know how to apply it. And I say, please do this with Control-C, Control-A. It says, yeah, you need to apply the lemma to this, and you will be done with this case. So that's good enough reason to go and do this lemma. Okay, now it's easier, because how are we going to prove this? Just about the only thing we can do is to do induction on the list of z's. So I say, please do this by cases on z's. What is this? Oh, this should be easy. It is. Control-C, Control-A. What about this? So first of all, depending on your psychological profile, you may feel it necessary that this should be a z instead of an x. For example, I do. Okay, so now what do we do here? Okay, thank you. Any ideas? Say again? You want to argue underneath concatenation with z. But look at the bracket on the right side. Look at this. Does this compute? Let's see first. Now it does. Okay. So it's important to understand which way this is written. This is written as, actually the parenthesis should be here. Right? So it is Cong underneath. So it's Cong, okay? And I want to say it's Cong underneath what? Let me write it the long way around. It's Cong underneath this. It's conc under the function which attaches z at the beginning. But there is a better way to write this one, because I could write it like this. But there's an even better way to write this one, because I can write it like this. This means do a cons, and then the second argument is not there yet, so you need to keep the underscore around, and now this means the function which attaches z at the beginning. And this is the recursive call, because it's a shorter list. Okay, now we do this one. Okay, what about it? I find it extremely annoying that I don't know which way the parentheses are. I don't know about you, but I find this annoying. So already up there, I was kind of confused about this. Which one has the higher precedence? So let's see. This one has precedence 5. And where is the other one? This one has precedence 5. Excellent. Okay, this one is right associative. This one is right associative. What does that tell us? Nothing. I'm still confused. Okay.
Does that mean it doesn't matter?
Does it matter? That's a good question. Okay. So let's see if it matters. So does this mean that no, it doesn't matter. Here it doesn't matter. Here it just means, okay, we take this and we attach one more thing at the end. And here this means we take this and then we attach, but here, it's right associative, so it's like this, right? I can't write it, but these two are clamped together because it's right associative. Okay, I'm open to ideas. You don't have to give a global plan. For instance, if you know how to make a first step, if you know how to make something with the left-hand side or the right-hand side, we can start. Certainly one thing we need to do is we need to bring the situation to a point where we can use the induction hypothesis, right? We need to manipulate something so that the induction hypothesis appears. So, but what is the induction hypothesis? The induction hypothesis will be that the opposite of two concatenated things is, okay, I need the opposite of two concatenated things where the first argument is shorter. So that's that, you see? This guy here is ripe for an induction hypothesis because I am in the case where the first list is x and x's, but I see in my goal something that the induction hypothesis could be applied to. So how about if I start with that? So let's try to first apply the induction hypothesis in here and see what happens. Okay, before I do that, I also want to think a little bit about what will happen. What will I get? Well, I will get opposite of y's, opposite of x's. Oh, it's looking good. It's starting to look like the right-hand side if I apply the induction hypothesis. So let's do that. And I say, please use, well, I find it easier to type it up like this. Now, what is it that I'm trying to do? I'm trying to apply the induction hypothesis. It already did something weird for me. Because here, this thing now suddenly looks slightly more normalized than it did before. Okay, so I want to, okay, let me return back for a moment to see again. This is my left-hand side. So I will just put in this left-hand side and say, this is my left-hand side. This is what I want to think about. No, it doesn't want me. It's very unhappy about this, but maybe it will be okay. Okay, so how do I apply an induction hypothesis here? Well, it's underneath something, so it's a conc. It's underneath what? It's underneath adding this thing at the end, which is underscore plus plus x. If I'm right, then this should be working. It's not working. Why not? Am I misreading the situation? No, I'm not misreading the situation. I think it's unhappy because...
Parentheses?
Is it? Let's see.
Around the x cons.
This one?
Yes.
Let's see. There is an insane amount of parentheses here. I don't think I need all of them.
You don't need to write one, two right.
Okay, Robert? Okay, this one. Okay, there was a parenthesis. And now it says, what do you want to do with this? I want to use the induction hypothesis. And then it says, on what? Oof, does anybody remember what it was? Maybe Agda remembers. Yep. Thank you. Where are we? We're here. Now what? Oh, but this is just a case of parentheses. I just need to reassociate parentheses, you see? Here the parentheses are this way, and because it's a right associative operator, here they are the other way. So I need associativity of, this is another lemma, isn't it? Associativity of concatenation. Now again, I could look for it in the library, or I could just write it out. Use these W's. I'm trying to avoid letters that I already reused, because then I think it's clearer what is what when you apply things. Let's do this right, this way, right? Plus V's plus W's is use plus V's plus W's, colon, okay, so use V's, W's equal question mark. First, I see if it was going to help, okay, before I prove the lemma. So this is going to be another reasoning step. And it should be exactly the lemma here, like this, but maybe I do this first, okay? And then it's going to be the lemma. And does Agda help? Yes, Control C, A. By the way, when it's totally obvious what these things are, sometimes you can replace them with underscores, which means you figure it. It just means like whatever it's supposed to be, that's it is, you see? And I can start deleting them, because the underscores tell Agda, I'm not telling you what it is, you figure it out. But if you delete too much, then it gets unhappy. Now it's unhappy. So you have to keep at least some of them. I would maybe suggest at the beginning you don't do this too much. Say, okay, it has to be this, and it has to be this, for use V's and W's. What will that bring me? Oh, I'm done. And when you're done, what you do is to say, QD, I'm done. You go down here and you say, you fill it in for me. No. Reload, first reload, I typed QED, reload, now you do it for me. Okay, so it's just this lemma.
How do you, oh, right.
Yeah, say?
Just wondering, how do we know when we finished? It doesn't tell us that the lemma isn't finished, but it does. So.
Yeah, it's telling us that the lemma is not finished. What is this blue thing here? I'm worried about the blue thing, but apparently that's just a glitch. Okay, so associativity, what should we induct on?
W's?
That depends on how plus plus is defined. Plus plus, if it recurses on W's, that will be a good idea. But if it doesn't, nope, it recurses on the first argument. So we should probably pick U's, and then it will recurse on this one nicely. Oh yeah, U's, because, or no, or W's, or V's. If we pick V's, then it will compute here. If we pick U's, it will compute here. If we pick W's, nothing will happen, I think. So let's make a bet. I'll go with U's. Let's see. Okay, this may be giving me a false sense of security because this one. Okay. What is this? Let's try to normalize a bit more. No, it's already normalized.
It's the same thing.
Is it? Are we already at the induction hypothesis? Is this just reassociating? Well, even see, this is where the proof assistant says, if you're good at this, you say, oh, it looks like an induction hypothesis. Is it? Yes. Okay. Do it yourself. Do it yourself. Do it yourself. Why is it red?
You would need to use the common operator.
We use the induction hypothesis on the exact same thing that we were trying to prove. Not good. The first argument has to get shorter. Try again.
If we Kong the function adding x to the front, perhaps.
By the way, this thing here, the parentheses are really like that. This is how the parentheses are. Does that give you an idea?
Can't we get the x out by just the definition of?
We should be able to get the x out somehow, yes. How? It should be obvious, right?
Yes.
Because of how things are. Okay, so let's try that. So I say begin. Okay, let me keep this around here. Okay, so we'll soon be done with this proof and then we can have a break. So okay, so where open, I would be tempted to open this reasoning at the top here so that I don't have to write it in each lemma separately. This one is already given, and you're saying that this should be equal. We know where we want to land, right? You're saying this should be actually kind of the same thing as what? As x. What was your idea?
Just x and then we switch the parentheses to the right, I suppose.
So that it would be like this.
Yes.
So this step you're saying should be easy.
Yes.
Okay, and the reason that it should be easy?
I think that's how it's defined.
Okay, let's see, because plus plus will recurse on the first argument. So I think maybe it will not say this, it might not do that, but it might do that. Oh, but that's the same. Okay, anyway, if we think that it's an easy step, then what we do is we write down this thing here, okay? We say, what? Okay, we say, we think it needs to be this. Oh, go away. We think it needs to be this. For what reason? Maybe. By the way, you don't have to write REFL here. If you think it's trivial, you do this one. This is a different operator. Okay? But the color is not nice. It's not very nice. I think we're on the right track, but maybe we need to do it in a slightly more careful way. Why? It's already blue. Oh, it's blue because I have one more step. No, it's just blue. Is this even the right thing? Let me start from the beginning. Sometimes I get lost like this. Okay, now there is no doubt that this is the right one. The blue will eventually go away. Let's stare at this first again. So this thing here is the same as x u's plus plus v's. That's okay. Okay. That was the idea that I think you had. But there is still this other plus here. So I think there is actually another lemma. I suspect the lemma that, okay, I said I wouldn't cheat, but I will cheat because we're running out here. It was a conc. Really? Maybe am I misreading the goal? When I got, at the very beginning, when I was here, here, I'm reading the goal. Is this cons twice? Cons and cons?
I think so, because they're...
There it is. Okay, I keep misreading this. Yes. Cons takes a lower precedence than plus plus. I think that's what I find counterintuitive. So this is actually cons followed by that, and this is cons followed by that. So in fact, it's pretty easy.
Don't they have the same precedence?
It's the same precedence, but for some reason it's deciding to show me parentheses in this way.
Oh, it doesn't
Okay,
mean that.
so anyhow, because it's a cons, okay, what I say is, look, we just need to use the induction hypothesis on the tails, you see? So that's use the induction hypothesis underneath the x cons, which is what you were telling me all the time, but I didn't understand you. Thank you. So it says use under this x cons thing the induction hypothesis. Victory. Okay.
By the way, I just noticed that we could have also inductive stepped on W's because we proved that just above the lemma,
Yes?
where it would have calculated just fine, I think.
Okay. So you're saying there's the possible other proof where you induct on W's and you use the upper lemma.
Yeah.
I think that will certainly do the base case for the W's. Will you have to worry also about the induction step to have another lemma? That's something for you to figure out during the break. So we're going to have a 15-minute break, which means I can't calculate this. 10 plus 15 is easier. 15:25. Okay, so I think these solutions here are sufficiently similar to the ones that I typed in so that you can get them just from here. I don't think this Emacs file that I created has anything there, but I could also include it here, but I think it's exactly the same. Okay, let's now go to the sort of the core of what I want to talk about today, namely dependent sums. I'll first explain the idea naively. So far, remember that when we have, this one, yes, so things have been randomly dying. Let's try to fix my tablet. The first rule of computer science is that things work better when they're plugged in. This can be a tricky thing, but I think it's plugged in. No? It's also wireless, so I could try to do it this way. Well, okay.
Is the pen out of ink?
No, I don't think so. Okay, so remember that we had the notion of a dependent type. I can tell that I'm on wireless now because it's lagging. dependent type, which is you have a map from some given type A into types, which in Agda are called set. But I'll write type here. So for each x in A, we get a type B of x. And we already saw the thing that we call dependent function space. Which we, in Agda, is written like this. But it's also written like this, or some variant of it. And it's even written like this sometimes. But that doesn't mean it's logic. It means it's also logic, not just logic. What was this? Well, these were functions where each x in A, so an element of this type is a function which takes an element x in A and gives you an element in the type B of x. That's why it's called dependent function space. This is also called dependent product. And it it's like the product of sets in set theory, Cartesian product of many sets. Okay. Now the dual operation to that is a dependent sum. And naively, set theoretically, you would write, which we would write something like this. And let me just write down what this would be set theoretically. Set theoretically, these are elements x, so pairs xy, such that x is in A, and then y is in B of x. This is called a dependent pair. Why is it a dependent pair? Because the type of y depends on x. That's why it's called a dependent pair. And it's also called, so this one is also called pi type. There is some very unfortunate terminology going around here. This one is also called a sigma type. But it's also called dependent pair type. Okay, so there's lots of terminology going on. We haven't really come to the unfortunate thing. We will once we get to Agda. So what is this thing good for? This is a very general way of packaging up information, especially in cases where this information, pieces of information, depend on other pieces of information. So that you need to be careful about how you order things, and then the thing that comes afterwards depends on the thing that came before. Let's have an example of this, just to get some feel for it. What we could do this. Let's do this parity example. So this, I think, maybe this I think I can do directly in the lecture. You can, oh, by the way, there's lots of good texts on sigma types. If you want to read, it's pointless for me to write down here like 3 pages about sigma types. They're also called existentials, by the way. So programming. So Phil Wadler's book, Programming Language Foundations in Agda, has a whole section on quantifiers, which I think is very useful to read. It will also give you a preview of what's to come, because he also explains the logical meaning of these things. And then there's also a section on sigma types in Martin Escardo's notes, so I recommend reading about these things. So let's do this using Agda, and let's do something with it. Now, here is the unfortunate thing. In order to use dependent sums, you need to import products in Agda. And then when you go and you look what this thing is doing, it says definition of dependent products, and then it's sigma. So they decided that this one also could be called dependent product. I don't know of too many people who do this, but the Agda standard library does. You can follow my Twitter discussion on this. So I will avoid using the word dependent product for dependent sums. So I'll try my best not to create further confusion. Now, we will look at the definition in a moment. Let's just try to write something down. Now, to have some substance, let's look at a very simple function, namely the parity function. So you want to calculate the parity of a number. 0, 2, 4, those are even numbers. 1, 3, 5, they're odd numbers. So you might, if you didn't know better, you might implement it like this. You would say parity is a map from natural numbers to Booleans. It maps 0 to true, and it maps the successor to the negation of the previous one. This has a problem. How do you know? So suppose I tell you that, so you have to keep in your mind the fact that true means even and the false means odd. This is not obvious at all, that true should mean even, because it could be the other way around. This is a very general phenomenon that appears in programming. If you use functional programming, you're less likely to suffer from it, but if you use imperative or object-oriented, then you will likely suffer from some form of it. It's called Boolean blindness, and there is a nice blog post by Bob Harper on this. So Bob Harper he's a major person in programming languages and type theory, and his blog always pushes all the right buttons for people to go crazy, but I think also his opinions are very much worth reading about. So lots of entertainment, but also lots of wisdom. Anyhow, it would be better if we did it this way. There is nothing wrong with defining a custom data type. Data types are easy. Just define them, use them. They're not heavy duty, okay? So you just define a data type which has two values called odd and even, and then you map 0 to even, okay? And then what do you do with the successor? Well, you need to know what the recursive call does. So this is the width, the additional width pattern. So it's a width parity of n, and now we're going to branch on this. If it's odd, then it's if the previous one is odd, then it's even. If it's even, then it's odd. Okay. Now this is okay, but it's still missing the complete mathematical content. The complete mathematical content here is that what we are really doing is we are decomposing a number. What is really behind this, the thing that would be the mathematical statement, is this. For every natural number n, there is a k and there is a b in 0, 1, such that n equals 2k plus b. So the function computes b, but it doesn't give you any evidence that this b has anything to do with anything. What we would like to do is we would like to say, no, actually, we computed the b from this theorem. That would be better, because then we would know that we didn't just compute a random bit. We computed. We have the mathematical correctness of our function. So here is an example of how you do this with the sigma types. You only need to pay attention really just to the first line. Okay, you don't have to pay attention to much of the rest. The rest here is more equational reasoning, which for some reason I found like really verbose when I did this. And you can entertain yourself with all these lemmas, and I would be glad to know if this can be shortened, say, like by a factor of 2 or 3, because it seems a bit long. Also, it's not the kind of thing that you want to do in Agda all your life. It's too low detail. Anyway, Here. This is the same theorem, and it's using sigma. How is it using sigma? It says, for every number n, we can have a dependent pair. The first element of the pair is a number. The second element of the pair is from this type, which depends on k, by the way. It's this type. What is this? Well, this is another number, another dependent pair. So the second component will really be a b, which is 0 or 1. And the third component will be a proof that the equality, the desired equality, holds. So this is packaging up information in the result. It's returning not just the bit, but also the other witness, the k, and the fact that they fit together in the proper way. So once you have this, you have a function which is returning a triple, and the second component is the parity. Actually, it's not a triple. It's a nested tuple. It's a tuple nested by another tuple on the second component. But because of the way reflexivity works, you can write it like this without parentheses. So this will put parentheses around here. Yes, you can write it. It's possible to write ordered pairs in Agda using just a comma. You don't have to have the parentheses because the operator is underscore, comma, underscore. So it's an infix operator. Yes? That's one idea of what you can do with sigmas. So here we see that it's carrying data, more data, and then what really amounts to a logical proposition. It need not be data. This kind of packaging is very important. So this is on the small scale, but you can imagine on a large scale, this is how we would encode mathematical structures, for instance. What is going to be a ring? Well, a ring is going to be sigma, 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 sigma something, because we'll say it's a type, and then it's an operation that depends on the type, and then there's another operation, and another operation, and then there's an equation, equation. So it'll be a long string of nested sigmas, each carrying some more components. As I said, I don't think we've seen enough equality proofs for today, so we're not going to go over this. So I already reviewed dependent types, so I don't have to do it again, but here is just conveniently, in Agda, dependent type is written like this, but I just defined the pi like this. Okay. Now, the next exercise that we're going to do regarding the dependent sums is we're going to look at how we can get the simple products and the simple sums using the pi's and the sigmas. Because this is sometimes confusing, because there are two ways in which you can get products. Actually, let's see. Let's do this first on paper. Well, I suppose it's fair to call this paper. So I'm just going to do all four possible cases, and the cases are as follows. So if I have two types A and B, I can consider the constant family, which takes, so the constant family which goes from A to type, which takes every x to the type B. So that's constant. This is the constant family, or the constant dependent type, where the type does not really depend on A. So that's one option. Now, what happens if so that's another, that's the one thing I want to look at. Let me move this thing up here, okay? The other one that I can do, I'm trying to predict the final picture here. I think I want this here. Look at this AI. Okay. And the other one is that if I have two types, A and B, then I can form a type family, which I will denote this way, double bar, and you think of it as A or B. And this one goes from bool to type. And the way it works is it takes, let me be in sync with what's down here, false to A, okay? It takes false to A, and it takes true to B. That's a family of two types, right? This is a Boole indexed family. Okay. There we go. Now, I have a dependent type here, I have a dependent type here. I can make sums and products. So let's make the sum of this one first. So what is this? This is going to be sigma of x in A of B of x. What are the elements of this? What do they look like? Naively speaking, the way you think of the elements is you take, well, it's something from the first component and then something from the second component, where, okay, x has to come from A and y has to come from, oh, by the way, this is not B of x, that was the whole point. It's not dependent, it's always B, yes? It's always B. For every x in A, I get B, 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 B. So this will be just B. So that's just going to be the same or isomorphic to A cross B. It's just ordinary pairs. Because there is no dependency, you just get non-dependent pairs. Yeah? Okay, what happens if I take pi here? Well, if I take pi here, that's going to be pi. Let me switch colors. It'll be better if I switch colors. It'll be visually separated. So if I take pi, that's going to be pi b in Boole of a b applied to b. So what's that? Well, that's a function. So what's an element of this? An element of this is going to be a function f which maps from Boole to the dependent type, and it's going to take false to some element which has to be in, so this thing, when I apply it to false, I get A. So false has to go to some element which is in A, and true has to go to some element which is in B. So it's a function from a two-element set. The first element false true. False is mapped to something in A, true is mapped to something in B. But you see that that's the same information as an ordered pair. That's the same information as ordered pair. To say I have x in the first position and y in the second position is the same as to say I map false to x, true to y. Yes? So this should also be A cross B. There are two more possibilities. I could also take a pi here, and I could also take a sigma here. It's written in the lecture note as an exercise, this thing. So I will let you answer this maybe during the break, or if anybody wants to think and answer on Discord. What do you get if you take pi here, and what do you get if you take sigma here? You get something that's isomorphic to previously known constructions, to constructions that you already know. So the question is, what is it? It's not too hard to figure out. Okay, let's actually see how one would prove that these isomorphisms hold here. Let's see how that works. So, how would you show that if you make a sigma of the constant family, that's the same as the pi of this two-element, the two-valued family? Here are the AGDA definitions. Maybe we can have a look at the code here. So first, this is the definition of the two-element family. So AB means it's the dependent type which maps false to A and B to true. Now, let's get rid of these and define together the isomorphisms. So the first isomorphism is the phi. This one, oh, by the way, this thing here is just a shorthand for sigma. This is actually just a shorthand. This really is just the constant family, you see? So in Agda, where am I? Here. In Agda, this is not an isomorphism. In Agda, this is the definition. A cross B is defined to be this sum. So we really just need to show that this sum is isomorphic to that pi, which is what we're showing here. This sum, which is just A cross B, is isomorphic to this pi. And I don't have to write bool here, but I could if I wanted to. It just knows that it's bool. Okay, so where do we map x, y? We want to map the pair. Let me do this in a way that is reasonable. Okay, so we want to map this pair x, y to the function which takes false to x and true to y. So how do I do that? I say Control C, Control R, and Agda says, yeah, you have to give me a function. And if I go in here, I says, yeah, x1 is a bool. Okay, well, it's a bool. Let me put, I can't live with an x1. Let's make this a b. So now I would like to consider cases. What are the two cases I need? What if b is true and what if b is false? There is a way to do the pattern matching inside lambda, which is like this. You put your lambda in curly braces. Now, once you have the curly braces, you can do pattern matching on b. So I say do pattern matching on b, and it will produce two cases. It says this is a function which is supposed to take false to this and true to that. Okay, so now no, this one goes to x, this one goes to y. So that's the function. Okay, how do we go the other way around? If I have the function f, how do I get an ordered pair? Well, the first component is f of false and the second one is f of true. So here I say Control C, Control R, which means use the constructor, and the constructor is pair. So I have to produce something in A, so I say, well, f of false, f of true. And I don't really need these parentheses. Agda put them in. Okay, so now, what else? Yeah, now we know. Now we want to show that phi and psi are inverses of each other. So how do we do that? Let's show. So you could show that let's show this, that for every element p of A cross B, phi psi of p equals p. So what happens when you try to do this? Well, the way you do it is you actually write this, okay? And then you say, well, but p is from a product, so I could do Control C on p. And then it gives ridiculous names, which when I feel the urge to change them. And now I need to show this. And if I normalize, it says, well, but this is just the same on both sides, so that's very easy. They do compute to identity. The reverse side is not so easy. In the reverse side, what you can show is let's see what we can do. So what we can do, we would want to show the other possibility as well. That is to say, if you do phi and psi and f, that you get f. However, for that, you need a principle called function extensionality, which I think was already mentioned in the exercises once before, was it? Yes? So let's see what this is. Here is a mathematical principle which is baked in quite deeply into mathematics. It says, if you have two functions, and for every x in the domain, they give the same value. So if two functions agree on values, then they're the same function. This is mathematically obvious. Nobody even questions this. But if you're a programmer and you think of f and g as algorithms or code that returns results, then you certainly are not going to think that they are really, really completely equal, because these could be two sorting algorithms, and one maybe works faster than another, or one of them uses more memory. So it makes sense in certain situations to think of functions more like code or programs. And programs or code, they carry more information. You can detect, you care about other things than just values. So as a programmer, you're going to say, well, yes, they're kind of equivalent if they return the same results, but that's not all there is to functions. So we're going to say maybe equivalent, but we're not going to say equal. Type theory doesn't make this decision for you. Type theory says, well, yeah, type maybe, because Agda is essentially a programming language. We shouldn't have function extensionality. And we don't. Agda does not have built-in function extensionality. But for the proof that we want to prove that these things are isomorphisms, which is a mathematical statement that we are trying to prove about mathematical functions, not about code. So what we can do is we can postulate function extensionality. So this means that in Agda, you add something without defining it. You say postulate, and you say, I'm going to have funX, which has this type, and this type is precisely what's written up here, namely, that if two functions have the same values, oops, nope. What happened? What did I just do? It was some three button mouse thingy. So it's just the transliteration of this. And then when you want to use the inverse, you need to use the function extensionality. That is to say, instead of showing that if I use phi and psi on f, instead of showing that I get precisely the same f, what I will show is that I get a function which behaves the same way as f. That's what this function extensionality allows me to do. So how does the proof go? So I start from nothing here, and I say, okay, we need to show this, but I know because of theory and other people wrote papers about it, I can't do this in pure Agda. I have to use function extensionality. So I say, please use function extensionality. And then it says, okay, but you have to tell me what the functions are. Okay, so well, the functions are, does it know? No, it doesn't know. The functions are phi psi of f, this is one, and the other one is f. And now I say, well, now you have to show that for every x, if I apply one of them to x, I get the same thing as if I apply the other one. So I say, okay, let's take an x like that. But now x is a Boolean, so I really should consider two cases. Oh, I know how to consider two cases for a lambda. I have to put this in brackets like this, and then I say consider two cases. And now I need to show this, but if I normalize, I see it's the same thing. So Agda just refl, okay? And here, refl. So this was a little bit of foundations here for us, which shows that we've actually seen that this isomorphism here between these two requires a little bit of mathematical thinking, and most of all thinking of functions as mathematical functions, not algorithms or anything like that. Okay, any questions? The exercise here is, what are the other two possibilities? What do they give you? You will see that the isomorphism that we have here, where is it? Here, is really now made up of 4 parts. Because first we defined 2 functions, and then we had 2 equalities that we proved, two further statements, namely, so an isomorphism is really 4 pieces of information. And this is something to keep in mind. When you do mathematics classically, you come to like my class in logic and sets. When I define isomorphism, I think it's probably in the 2nd lecture, what do I say? Well, I say an isomorphism is a function f for which there exists an inverse. And we define what an inverse is. And then you think that an isomorphism is a property of a function, which is correct. It's a property of a function. But there is another way to package it up. You could package up the whole thing together. A function, its inverse, and both proofs that they are inverses, both ways. Then you get a package which is nicely symmetric. Because now it's going to be, you have everything at your disposal. You You don't, you know, if I just tell you that it's an isomorphism, where are you going to get the inverse from? You need something to get the inverse from if you actually want to get the inverse. So if you package things up this way, then the information is available and you can use it, which from formalization point of view, programming point of view is convenient. So we could package this up. We would use this, we would use dependent sums. As I said, you can package things up using the nested dependent sums. So here it is. It'll be more, probably more readable down here. It's not really that readable. Okay, let's at least have it on one line. This is the type of isomorphisms. So here's another thing. Usually when you say the sets A and B are isomorphic, you think of that as a relation. But now we're going to think of it as a structure. We are not going to say types A and B are isomorphic. Instead, we're going to say the type of isomorphisms from A to B. And then if this type is empty, A and B are not isomorphic. If this type has some elements in it, then A and B are isomorphic. But the point is that we are keeping all the elements. So we will know all the ways in which they are isomorphic. So this is similar to changing the view of logic, where you say, instead of saying that a statement is just true or false, let's think of a statement as the collection of all its proofs. So you're keeping all the reasons why the statement holds. You keep them around so that you can analyze them. This is similar. Instead of just saying they are isomorphic, you keep around, you say, no, I'm just going to look at the collection of all the isomorphisms. I'm not going to forget what they are. So then I can always say, oh, I mean this one or that one. There will be interesting structure. Presumably isomorphisms from A to B can have an interesting structure. And we know that. Because if we look at isomorphisms from A to A, we get group theory. So it's not, yeah, it's a good idea. Now, but how do we do this? Well, I just nested things. I said sigma. So it's going to be, let's see, is it a triple, a quadruple? It should be a quadruple. So it's a triply nested sigma. The first component is phi, which goes from A to B. The second component is psi, which goes from B to A. The third component is here, but the fourth component is independent of the third component, so I can use cross. I don't have to use sigma anymore. It's the first equation, and this is the second equation. Yep. This is used a lot everywhere, but not in this form. There is a better form called record types. And so that's what we're going to do in the next hour. We're going to look at the record types. And now, yeah, we can have a break because this is a good breaking point. We're going to look at the generalization of sigmas, which don't, mathematically speaking, the record types are not going to bring in anything new. Mathematically, record types are just a bunch of nested sigmas. But for a programmer and for somebody who actually wants to work with these things, it's quite important that you have record types instead of nested sigmas. It's like the difference between being able to use variables with names and having to use memory locations. The difference is as big as that, because when you have a sigma, you have the first, second, third, fourth, fifth component, and you have to keep it in your head. The sixth component is this, the seventh component is that. That's like working with raw memory. But with record types, we get to name the components, and we will see this next hour. So a break for 15 minutes. Did you figure out the answers here? Let's just... Dead again. All my hardware is breaking. The mouse in the office is not working. This is not working. So, what do we get if we take the dependent, the constant family, and then we take the product? What's it going to be?
Function type?
Yes, from what to what here?
From A to B.
from A to B. Because, well, it's functions that take elements of A to corresponding types in B, but it's always B, so it's just AB. What do we get here? The sum, the thing that we usually call A plus B. Why is that? Because let's think about what an element is like. So an element, so this one is more interesting to look at. So I have sigma B is in bool of A, B, B. So an element is going to be a Boolean. So one option is that it's a false and an element X from A. The other option is that it's a true, and then it has to be an element Y from B, because it has to be from the correct type. But the information here is just the same as the information that you have for an ordinary sum. This is the tag. False is telling you it came from A, and true is telling you it came from B. So injection 1, injection 2. Right? So you see that you can get these things here. And the part of the confusion about the terminology arises from the fact that the products, the simple products, can be obtained in these two ways. And then people say, well, but if sigma is a generalization of product, it should be called product. Well, by the same reasoning, pi is a generalization of product, simple product, so they should both be called products. That's not going to work. Okay? So I never bought this argument because in the non-dependent case, sigma corresponds to product, should be called product. It doesn't work. I don't know. Why? Anyhow, let's go on. So what are these record types? Let me explain the idea from a couple of points of view. Let's do the programming point of view first. So I don't know if you were in principles of programming languages, you probably heard this story before. But as a programmer, you might be bunching together lots of information. So one way to bunch together information is to just make a huge tuple. So you make a tuple of stuff, and then you have lots of data. And then you have to remember, so if this is an element like this, so think of a case where this is like a row in a database, and so this is like name, last name, date of birth, date of registration, okay? 17 components. In principle, you can work like this, but you will always, as a programmer, you will always have to keep in mind the numbers. Which component carries what information? And that's silly, and nobody does that. Instead, what we do is instead of calling these components the first, the second, the third component, why not give them names? So you give them reasonable names. So when you have a database, you don't have the first, the second, the third column. What you have is you name the columns. So you have name, last name, and so then you know what's going on. Well, but we can do this exact same thing also in a programming language. So instead of doing that, we would say, we just name them. So we say, okay, so suppose this one is name. So this will be like, this is the name. The last name is this. The birth date is this, and so on. And this is usually called something like a record. It's called a record. And these things, one of these things is called a field. And that's this thing here is a label of the field. You label the fields, and I only have some fields, and they get records. A record type describes this structure. So the record type will tell you which fields you have, what their labels are, and what their types are. So you will say, aha, I have a field called name, and it's a string, and I have another field called last name, and it's also a string, and so on. So that is the corresponding type. It's describing the values, which are the records. This is a programming concept. You can find this in many, many places. So this is in C, this is a struct. In C++, it's still a struct, right? In OCaml, it's a record type. In Haskell, it's a record type. That's because the people who invented record types also invented these languages. So where else? In something like something more object-oriented, like Java, well, in an object-oriented language, you represent everything using objects, so records will just be objects. And you might be wondering, aren't records just exactly the same thing as objects? And the answer is no. Objects have an additional feature. They can refer to themselves with this. So they are like recursive records, records that can refer to themselves. So there is a strong similarity, but objects are a lot more complicated, even though, yes, they are a kind of records. Do we have records in mathematics? Yes, of course. So, but you have to be very careful with mathematicians because they really like to be dishonest about how they do things. So, for instance, a mathematician will tell you, what is a group? And they'll say, well, a group, they'll say, it's a quadruple. They'll write something like this. They'll say, it's a quadruple, where this is a set, this is an element of the set, this is another binary operation. Okay? But then, they're not going to say the third component of a group. They're going to say, we call this the unit. We call this the carrier. And they'll give names to these things. This is multiplication or operation. And this is inverse. So mathematicians also use records, but they don't know that because they were only taught set theory, and then they don't know how to do this. Luckily, lots of mathematicians are learning how to use proof assistance, and that they'll set this record straight. So I'm expecting in about 20 years the situation will be much better. But nevertheless, they do this. They have a structure that has components, and they give them names, and that's a record. And the type is the corresponding record type. You can try any other one, and they'll all be like this. So, for instance, you could say a topology. Well, it's two components. No, actually, we're not done here. Where are the axioms? So there are more components here that they don't know about, because they put them on the side somewhere, but they should put them in here, plus axioms for group theory, axioms for a group. So if we're very careful, we need to put the axioms somewhere. Well, it's very easy to put them anywhere on the whiteboard or in some place on the paper. But if you're going to do this in a proof assistant, you need to be slightly more organized. So you will quickly realize that the axioms should be part of the structure. And they should be there. So that's the use of records in mathematics. And we will practice this kind of structure next time, but I'm giving you a preview. Another kind in programming is when you package up a data type. So if you say something like a dictionary. So a dictionary is a data type plus empty dictionary, a function that adds stuff to a dictionary, a function that looks up things in the dictionary, a function, right? I'm naming parts of a larger structure. Whenever you have a structure which is made of parts, there's a good chance that you want a record, especially if those parts have names. So much of the general idea. So let's have a look at how this is done in Agda on a concrete example of Gaussian integers. Now, you all know about complex numbers. Gaussian integers. So the one way to think of complex numbers is it's the reals to which you add the unit, the imaginary unit, so I, with the law that I squared equals minus 1. The Gaussian integers you get if you take the integers and you add the unit. So they will have the form a plus bi, where a and b are integers. So that's what the Gaussian integers are, and I'm pretty sure somebody told you about them in algebra, but just in case, let's review this. So you compute with them just like with complex numbers, except that both components are integers. Why did I do this? Because Agda's standard library doesn't have reals. Reals are not such an easy thing to formalize, and the standard library of Agda doesn't have reals, mostly because the audience, the Agda audience is programmers, logicians, and people who don't generally feel an urge to formalize the reals. So that's why we're doing the Gaussian integers. Where are we? We have to go up, 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 here. This is how you write a record type in Agda. Record, you give it, this is the type, I give it a name, and because I'm in Agda, I can play games, so I'll have a funny name. So Gaussian integers are the integers to which you adjoin I. It's kind of neat, okay, so that's the name. And then you say, well, what set level it is. We still need to address properly the set levels, but we just say now, okay, we're defining something that's a type. And then here is just the basic usage. There are two things, and none of them is necessary. You can have a field called constructor, which tells you how to make elements of this type. So because I declare the constructor, if I write two integers between these triangle parentheses, that'll be an element of this type, and of course these two underscores correspond to these two components, the fields. So below you have a field declaration, and you just list all the fields with their types. So here in this case we actually see a record where the two types are not dependent. This one doesn't depend on the previous one, but later we'll see dependent records where the field types depend on the previous fields. So we have two components, the real and the imaginary component, and they are integers. Questions? So let's see how this works. Okay, this is explained here. Now, as it turns out, whenever you define a record, this secretly also defines a module with the same name. We will see the next time that you can put inside the record, you don't have to put just the constructor and fields, but you can also put arbitrary additional definitions. And so then it works like a module, and that is useful. But this is a simple case. Nevertheless, you have to open the module if you want to be able to write RE and IM. Otherwise, you have to give the name of the record type .RE. You have to fully qualify the name if you don't open. So this open here is just so that I get access to everything that is in the record type. See? So now I'll be able to write RE instead of this horrible thing which I don't want to write. So let's define a function. And this is a good case of doing it from scratch, like this. So let's define addition, which I call plus g for Gaussian integers. So it'll take two integers, it'll take two Gaussian integers and return an integer. Here it is. X plus y is what? So now you have to know how to produce something of this record type. There are two ways. I could say use the constructor. And then it says, okay, what's the first component? And what is the second component? And now I say, well, the first component is RE of x plus RE of y. And the second component is imfx em_y. That's the first way of doing it. The second way of doing it is, if this one is useful when you don't have a constructor. So if you don't have this one, there is still a way to construct the record. And the way you do this, so I will just press Control-C, Control-R. No, oh, it knows that this is the constructor. Okay, I'll do it with my bare hands. You write record, R is this, comma, is that. No. Which one am I? I'm so used to Agda doing this. Okay, it has to be a semicolon. So you can say, I'm going to have a record, and then you give the values of the fields. So that's the other way. This one also works. It works always, even if you didn't declare a constructor. And now you say, well, it's REX plus REY. And this one is imx plusimy. That's one way to do it. That's the second way to do it. Now, we could also do a third way, which is shown here, with subtraction, but nonetheless, let me do it here, okay? So, I might get tired of typing REX, REX, REX. Well, I can just say, please, pattern match on X. And it's going to give me, for X, it's going to give me the both components presented in this form as a constructor, the real and the imaginary part. And then I say do the same thing for Y. And now I'll call this one X2, and this one I'll call Y2. So now I say use the constructor, Control C, Control R, and I can just write X1 plus X2. No? What? Okay, I forgot to load the file. Y1 plus Y2. What happened to the keycaster? It's not showing up, right? It's not happy. Maybe now is not the time to. Okay, not gonna try to debug it now. That was yet another way to work with constructors. So you can pattern match on the input already. There is a third one which is called copatterns, and that one works as follows. You say, I want to define X plus Y, and I need to give the real and the imaginary component. I will give each component separately by saying the real component is this, and the imaginary component is that, like this. This is called co-patterns because I am putting sort of patterns on this side. It's kind of dual, where I am pattern matching on the output instead of the input. I'm explaining what the components of the output will be, not the components. I'm not looking at the components of the input. This is a feature that Agda has. It behaves in a little somewhat funny way. So sometimes it's a bit surprising because it has something also to do with co-induction, which we haven't spoken about. But you will see the pros and cons of this also in exercises. Anyhow, so now I can say, well, it's REX plus REY and IMX plus IMY. So that's yet another way of doing it. Sometimes the copatterns work well. So these are all the three ways. So now let's see. Here I have the patterns. Here I have the copatterns. So if I am restoring plus, well, I could just restore the plus to its former glory. What was its former glory? Oh, I changed things around here. Okay, never mind. This one, this was its former glory, so let me use this one. There we go. I just didn't want to change too much. Subtraction, this is just things done in different ways. Okay, so that's an example of how you can work with copatterns. Let's see what else we can do. Let's define I. Okay, so how do you define I? I say, I'm going to define a Gaussian integer. It has two components, and now you need to know how to write down integers in Agda notation. So the library for the integers has this notation, which is a little bit funny. Well, it's not that funny. You'd say plus, and then you give a natural number, and that's going to turn it into an integer. So if I write plus like this, an integer, that will work. Why is that? That's because up here, somewhere, I opened the integers. You see, I opened data integer, and this thing has now it also opens data integer properties, and it pulls in a bunch of things. And another thing, one of the things it pulls in is that plus has this, that there's this notation for plus. Okay, so that's I, because the imaginary component is 1 and the real component is 0. Let's prove that I squared actually equals 1. So how do you do that? So from scratch. So the way that I want to do that is I want to say, I want to prove this equality. I times I equals minus 1, 0. This is a very funny notation for negative numbers. Plus 1. That's the reason. That's because of the reason that the integers are defined in a slightly strange way. But if you want to have the negative integer minus 1 plus n, then this is what you write. So this is minus 1. Yes, it's silly. Yes, we wouldn't really want that in a real programming language. I agree. How are we going to prove this? Well, first of all, we could try to just say REFL, right? And it works. Because it's computed. But let me also show you what would have to be done in case that it's slightly more complicated. We're trying to prove that two records are equal. So how can you prove that two records are equal? Now here's an important thing about records. Agda says that two records are equal if they have equal components. So we just need to convince it that the components are equal, which means that we need to show that the first component of this one equals the first component of that one, and the second component of this one equals the second component of that one. But that means that we're trying to prove that the arguments to the constructor are equal. So that's a case of Cong. In fact, it's a case of binary Cong. Binary Cong says if you have a function of two arguments and you want to show that f of x of u equals f of y of v, you need to show that the first arguments are equal and the second arguments are equal. So I'm using that, and I will apply it to the constructor. That's how you convince Agda that you are going to show that two records are equal by showing that each component is equal. You say Cong. Now, if you have three arguments, you need Cong 3. So it's a bit weird, but doable. So now it's asking, why is the real component, so this is the real component, why is it equal? So here I can just say, do it yourself. No? Oh, it doesn't want to do it myself. Okay, that's okay. I mean, of course, the REFL proof was better. I'm just showing you how to prove that two things are equal if you have two records. Let's look now at the definition of the unit type as a record type. This is defined in data unit, and it's defined like this. It says it's a record type, and it doesn't have any fields. It only has a constructor, which is called TT. So this is an empty tuple. And the way you construct it is you say TT. In something like, in some programming languages, it would probably be just like open curly braces, closed curly braces, or something like that. So it's an empty tuple. Therefore, two elements of this type are equal if they have equal fields. But there are no fields, so this is vacuously true. So Agda believes that all elements of this type are equal. Let's try. So, by the way, this was our original inductive definition of the unit type, which said it's a type which is generated just by a single constant. And so that this is the only rule, so the only element is star. Here, there is an element called TT, and it's the only element. So we have, these two types they're going to be isomorphic, but there is a difference in how they behave. And this is what I'm trying to explain. Why did this thing jump? Oh, because I went back to where okay. So let's look at this. How do you show that all elements of this type top are equal? Here, because Agda believes that they are all equal already, because it says, well, X and Y are elements of a record type. So if somebody says REFL, all I need to check is that they have equal fields. Oh, but there are no fields to check, so it's okay. I could also do this. I could also pattern match. I could also say, what could X be? Oh, it has to be TT. What could Y be? Oh, it has to be TT. Oh, now it's a REFL. This also works. But the point is, this works. Because of the way the extensionality principle for records. Records are equal if they have the same parts. An extensionality principle will, in general, always say that two things are equal if they are made of equal parts. We had earlier the extensionality principle for functions. Did it say that two functions are equal if they have equal parts? Yes, because it said a function is made of its values. It maps x to something. It maps x prime to something. These are the parts that the function is made of, the pairs. right? And this is precisely what the extensionality says. If they're equal, they have to have equal parts, then they're equal. So here it's still the same. Okay, so now if we try the same trick with the inductive type, xy, then it's not going to work. And I think some people in the exercises were wondering why this is the case. So if I try raffle here, it's not working. Why is it not working? Because the way Agda computes with the data type, it says, if you want to do something with elements of the data type, the way you do it is you look at all the cases. A data type is always generated by some number of constructors. So, if you want to do something with the elements, you go and you look at each constructor and explain what you're going to do there. So, I'm trying to prove that all elements are equal. All elements of this T prime are equal. How can I do that? The only way that Agda knows of proving things about or computing with these elements is you have to consider the cases. That is the point of having an inductive data type. An inductive data type is generated by the cases, the constructors. So it insists that in order to compute anything useful, I have to do what could x be, what could y be. Now it says, oh, you did consider cases. I'm happy to look at what you're doing. Right? This is an important way. It's the same type, morally speaking, but the designs are different. We earlier said that we should be able to package up isomorphisms, not as nested sums, but as structures. So here we have our first example of a dependent structure. So how will this work? As I said earlier, so I already used this one for isomorphism, so now I'm going to use a slightly different one, this one for isomorphism. So it's the isomorphisms from A to B. What is one isomorphism from A to B? It's a thing that consists of 4 parts. A function from A to B, a function from B to A, the proof that the functions, so here is the dependence, you see. This field, called from circle 2, depends on the previous 2 fields. It mentions them. So it's a dependent type, so this is a dependent record. And these are the 2 equations. And now you can package this up and you can work with isomorphisms as structures. And again, many would say that A and B being isomorphic is a relation, but we're following a very important principle that says don't throw away structure. The relation of being isomorphism arises when you forget that there was additional structure, namely, which isomorphism was it? Keep the isomorphisms around. Don't forget the information. There's a whole chapter on isomorphisms in the book, so I recommend reading this because it explains things that I didn't explain, and it's generally good to look at many sources. Let's do something with the isomorphisms. First of all, the one that we had earlier, which had 4 parts, the one that we just defined earlier. Let's see how we define it here. Okay, so we say, now the new way to do this would be, given any 2 sets A and B, let us show that A cross B is isomorphic to the dependent type, and this could be bool if we wanted to, for clarity. But it doesn't have to be because Agda knows it's bool. And then I have to open the bool, so I'm not going to do that. So now, you're faced here with, hey, how do I do this? Well, you are trying to give me an element of this type. An element of this type is an isomorphism. It's a record type with 4 fields. I press Control C, Control R, and Agda says, okay, give me 4 fields, and I put everything on a single line. So now we have to work. I don't know, there is no universally accepted way of indenting this stuff. I used to indent it differently. Then, at some point, I started indenting it in this ridiculous way. I don't know. And now we have to fill in the fields. So one of them was, oh, but now I don't remember which one was phi and which one was psi. So let's go look. Actually, it doesn't matter. It'll tell me if I use the wrong one. Phi. Yep, happy. Psi. What was that thing called? Inverse something. Nope. It had to be the other one. Inverse. There we go. Inverse. Oh, now it's like this, and I'm done. And this is now all packaged up neatly. Questions? Let's do the identity isomorphism, but this time I will use copatterns. You see, here I defined the field. I use this record notation to give you all the 4 fields, 2 from 2. I could also do it with patterns, in which case this is going to be extremely boring, but just to show, okay, I go auto, no? Yes, I have to do this way, okay? So identity, in one direction it's the identity, in the other direction it's the identity, in this direction, this is trivial, this direction, it's trivial. So I was just pressing Control CR and A. So that's the identity isomorphism, and it's super easy to show that they're inverse. The 2 identities are inverses of each other. Here's the inverse isomorphism. I'm not going to retype this one, but you take, this is nice, very nicely symmetrical. If you want the inverse of f, where f is an isomorphism from A to B, then you just turn around everything. You swap from and to. No surprise there. And how about composition? Well, here's composition. Suppose, so we want to do composition, let's use copatterns again, just to get used to things. So I have A, B, and C, and if I have an isomorphism from B to C and another one from A to B, then I can get one from A to C. So the order is strange because that's how we normally compose things, right? G composed with F. So now I have to explain how to do this. Well, how do I compose GF? What will be the forward direction? The forward direction is just the composition of the forward directions. What is the backward direction? It's the composition of the backward directions, but you have to do it in the right order. So now F and G are swapped. And then here, we have some equality reasoning, which I'm not going to do at this moment. It's not difficult. You just have to use the 2 equalities. You see, you use one of the equalities on G and then on F, but the first time you do it underneath something. So it's not complicated, and I recommend this as exercises. I'm not going to do now. It's not very illuminating. The point is that you can define, I'm now doing this with these copatterns, so it's still packaging up everything in a single record, but it actually looks like 4 definitions. Okay, here is, I think, our last thing for today. Yes, so let's do another one, which is, remember we were talking at the beginning about decidable predicates, when I was saying when you have a predicate, one good way to think of a predicate is that it's mapping into Booleans. And when it maps into Booleans, you can actually calculate with it because you can see whether you got true or false. But the more general thing was that you have a predicate which maps into types, right? So that you observe the type of all the proofs. And then we said the predicate is decidable if it also has this Boolean function. So how would we really do that in Agda? Here's one way, and then the standard library has a still slightly fancier way, which I leave for reading. So let's do it. Let's look at this here. First of all, let me give a little bit of constructive mathematics here. So suppose somebody tells you this: a type A is decidable if either it has an element or it's empty. Then your first instinct is going to be, oh, but every type is either empty or it has an element. But for that, you need classical reasoning. You need excluded middle. If you're doing this thing in Agda, and then you will actually have to provide evidence of which of the 2 options happened. But in Agda, everything you do in Agda can be computed. So this evidence will be computable. So in Agda, this is really going to be you can actually compute an element of A, or you can prove that it's empty. It'll be one of those two things. So the corresponding definition in Agda is going to look like this. When is a set decidable? By the way, this will also feature tomorrow in the exercises. So when is a set decidable? There are two options. One is, yes, means it's inhabited. You give me an element of A. If you give me an element of A, that's one option, and now I know that it has an element. But the other option is that you give me a proof that A is empty, because a map from A to bottom is a proof that A is empty. The only way you can have such a map is A if A is empty. So this is, so in fact, the fact that A is decidable is an element of this data type. Now, of course, if you give me any specific type, I will be able to either write down an element, or I will be able to prove that it's empty. So it still looks like every type is either empty or decidable. Because of that, I give you here for further thought, and I would like you to think about this on your own, and then we can discuss it next time. If anybody wants to have an opinion about this, is this business of computability only shows up, it doesn't show up when you have one particular type and you're asking, is it decidable? It shows up when you have a family of types and you are asking, are all of them decidable? So here is an example. Here is a type which depends on a function. So take a function from n to booleans. So this is an infinite sequence of bits. This is the type which has an element. What's an element? It's a natural number n together with the proof that f of n equals true. So it's reasonable to call this attains true. Attains true of f means f is true at some argument, somewhere it's true. Yes? Now I ask, if I give you a particular f, if I give you an f that is like, false, 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 true, false, 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 well, you will just count which one was true, and you'll give it to me. So for a particular f, of course you will be able to show that attains of f is decidable. But if you state for all f attains true is decidable, now what this says is you are going to produce a computable function in Agda which takes a function from n to booleans, and it will decide whether it attains true. Good luck with that. How are you going to do that? It's going to be difficult, maybe. How will you tell whether a function f from natural numbers to booleans is ever true? Right? Something fishy is going on. So this is where you can actually see how this computability business becomes non-trivial. Even if you're thinking that each particular type happens to be either inhabited or empty, once I ask you, give me parameterized evidence that this is the case, then it may get tricky. Now, let's keep going. Let's say that A has decidable equality when this type is always decidable. So when for all x and y, the type x equals y is decidable. What does it mean for a type to be decidable in Agda? Let's define this. So a decidable set is going to be a what? It's going to be, first of all, it's a set. So this is the carrier set, which is called D set here. And it has to have evidence of decidable equality. Here, the next field is evidence that it has decidable equality, because it says for all x and y, it is decidable whether x equals y. Notice how this says here set 1. This has to do with levels. Because here I have something at level 0, because if I just say set, it's the same as set at level 0. Because I have something because the elements will be sets at level 0, then the whole collection of these will be at the next level. I promise we will do universe levels at some point, but they're really not that complicated, and I think you should be able to learn a little bit about them by osmosis. Excellent. So, questions about this? This is another example of how we package up information. Let's see one of these. It's how to prove that you could try a particular example. Let's try a particular example. Let's show that the natural numbers are decidable. So the way that you would do this is, let's see. I don't want to delete this one and do it with bare hands from scratch. Let's have a look at this, and I will say how I did it, okay? So I define a record, and I say the set is the natural numbers, and then I have to do this test, and I just did it as an auxiliary function, t. And this auxiliary function has to, given two natural numbers, m and n, it has to decide whether m equals n. So why are 0 and 0 equal? Yes. For what reason? Reflexivity. Are 0 and successor equal? No. For what reason? A function which Agda understands that there are no cases to consider, and so it already knows that 0 is not successor, so it says, yeah, it's a trivial function, and so on. And how do we do the recursive case? We say, for the recursive case, we first decide whether the predecessors are equal, and then if the predecessors are equal, that will force the successors to be also equal, and the predecessors are not equal, then here we need to construct a proof that they are not equal. This is the only interesting bit, but I'm not going to dwell on it now. Here's another exercise. If A and B are decidable sets, then we can construct the decidable set whose underlying set is the Cartesian product. So Cartesian product preserves decidability. How do you do this? First of all, you pick a smaller font. So this is now with copatterns. I'm randomly switching between copatterns and records just to get you used to both of them. So the underlying set is the Cartesian product, and now you have to write the test that tests whether two pairs are equal. What do? You call recursively on both components. You compare recursively the components of the pairs, and there are 4 cases to consider, but you can pack them up into 3 cases. If both components are equal, then the answer is yes, they're equal. If the first one is equal, but the second one is not, then you say it's not, and you have to produce this function here, which Agda, I think Control-C, Control-A, basically, Control-C, Control-R does most of this job. And then there's the 4th case where they differ already on the first component. Maybe let's do this one, okay? So you get to this, let's just see. You get to this point in your proof. So the first one is easy. So how do you do one of these no's? Okay, you stare at this and you say, hey, what is this telling me? It's telling me that x1 and y1 are not equal. Well, but then the pair x1, x2 cannot be equal to y1, y2 if x1 and y1 are not equal. So I say the answer is no. But then Agda says, yeah, okay, but now you have to show me that if they are equal, then bottom follows. So I say, okay, how do I do that? Control-C, Control-R. And Agda says, well, now assume they're equal, derive contradiction. And I say, Agda, yes, this is fine. But how about if I consider what this x could be? So I have to put this in parentheses, and I say, what could x be? And Agda says, well, it can only be reflexivity because it's an equality. And I look at this, and Agda says, well, you still have to derive a contradiction, but now y1 equals x1. So I stare at this and I say, oh, look, p, this assumption here that the first components are equal, this could be helpful. Can I use p? And Agda says, yep, you can use p. And then I look at this and I say, why is x1 equal to x1? Agda, do this for me, and I'm done. Here is the last thing that we want to do today. Let's do this. Given a list of elements, I think it's easier to see here. Given a list of elements, we can always attach a new element, but let's have an add function which adds an element to the list only if the element does not yet appear in the list. So it has to scan through the list. If it finds the element, it just says, okay, I don't have to add anything. But if the element is not there and it comes all the way to the end of the list, then it will add it at the end of the list. This function has a neat property that if the list didn't have any duplicates, once I add something to it, it still doesn't have any duplicates because it will never add the second copy of an element. How do you do this? Well, in order to be able to do this, you need decidable equality. You need to be able to decide whether x and y are equal, because when the function scans the list and it's looking at some element, it has to know, is this element equal to my x or is it not equal to my x? It has to make that decision. So I need to work with decidable sets. So here they are. We want add. We work with a decidable set. We take a list of elements from the underlying set. This is the underlying set of elements. And we take one more element, and then we'll produce a new list. How do we do that? So let's not look at that. Add. Okay, I have a list of x's. I have an x, and I'm trying to add this x. It's in this order because x will end up being at the end of the list. That's why it's at the end here. And I say, what could these x's be? It says, well, it could be empty or it could be this. And of course, this is unacceptable to me. I have to do this like this. I can't bear strange things. Okay. So what needs to be done here? The list is empty. Well, if the list is empty, we should definitely add it to the list. So we get the list which has just x in it. How about this one? For this one, I need to compare x and y. How do I compare x and y? Well, I can compare x and y using the test. Well, on what set? It has to be a test on the decidable set A. What am I comparing? I want to compare x and y. This should be width. Width. And then this bit I have to do with my bare hands, like this. It doesn't know what A is because I never gave it A. So here's A for you. And now I say, okay, we compared the result. What are the possible results of the test? And it says the possible results are yes of something and no of something else. And I go in here and I say, okay, this is the case when x and y are equal, but what is p? And it says, well, p is some x equals y, okay. I could also pattern match on p here if I wanted to. I don't know if this is not really necessary. What is the answer? So the answer should be, it's the same list. So I discovered that the first element of y equals x, so I should just return the same list. What if they are not the same? If they're not the same, well, if they're not the same, then I need to skip y, and then I add it to the rest. And now I see that I don't need to look at q, and I don't need to look at this. I don't need to look at the reasons. Did I create the same code twice? Yes, except that this one here, it's called ds. It's called A here. Okay, so up to alpha renaming, it's the same thing. And somebody's calling me. Okay, 1704. The decidable predicates are also defined in the standard library in a fancier way. You are welcome to click on this and wander at the code. That's it for today.